So we also have, of course, an integral form. We have an integral form for our Maxwell equations. We've got that by the divergence theorem, if I integrate over a closed surface the dot of the normal vector times d, what I'm going to get, this is just a generalization of Gauss's law in integral form. I've got the total free enclosed charge. Okay? If I do the same with the magnetic field, then of course I've got the total free enclosed magnetic charge, which is 0. Okay. And then if I use now the integral of Faraday's law and use Stokes's theorem, what I get is that I'll have the closed integral over a certain path of the electric field. And as before, this becomes the time derivative of the flux going through the surface, which is just the surface integral of the magnetic field B going through it. Okay, that hasn't changed from before. But now I can do exactly the same thing with the Ampère-Maxwell in matter. And again, applying Stokes' theorem, integral over a certain path, dl of the dot with H. This is going to be the total free enclosed current plus the time derivative of the kind of what we could call the displacement flux in there, A dot D. Okay, so again, this is like a green box, kind of real festival of green boxes today. Yeah, nice. So let's do that properly. Right, so you're comfortable with the derivation of all of these here. Right? So I don't know if that's a question or a statement. I hope it's a statement. Okay, and maybe just before I give you a break, just 2 more minutes. So we can just discuss boundary conditions. So that's the thing I've told you in the past. I really want you to be able to derive these boundary conditions at interfaces that come from these things. You remember there are 2 things that you can do. You can do the divergence theorem using this Gaussian pillbox, or you can do the kind of Ampère loop trick here. So let's just do that very quickly. So boundary conditions or boundary discontinuities. Okay, so once again, let's imagine I have a certain surface here, and on this surface I have a certain free charge density sigma f. So this is a free surface charge density. So what do? I take a Gaussian pillbox like this, right? You remember the trick. Essentially, if I do like 1, 2, 3, 4. So 1. If I take this Gaussian pillbox, and again, I kind of slice it such that it's very thin and straddling both sides of the surface here, then what do I get? I get that the D, let's say in the upper minus the D in the lower, dotted into some differential dA like this, which is this infinitesimal here, that this has to be just sigma free times the area of the little bit. So that's a little area A. So what this tells me is that the perpendicular component, maybe I should write above. minus D perpendicular below. This is just sigma F. Okay, it's just precisely the same reasoning that we've always done, now just with different symbols. If I do the same thing with 2 tells me that, as before, the B perp above minus the B perp below is equal to 0. Okay, so that's the first thing. Now, if I now take my surface again like this, okay, but now let's say that I have a certain, let's do a little Ampérian loop like this. Okay, so that's my path P, over which I will integrate. This branch is above the surface. This branch is below the surface. If I do this integral over this the Ampérian loop of the third equation, then essentially what I'm getting is that let's call this vector here L. What I'm getting is that the E above minus E below dotted into this displacement L, this has to be essentially given to me by the flux going through this little surface defined by this, but my surface is infinitesimal. Okay, so this goes to 0. So therefore, what this tells me is that the parallel components of the electrical field, so the meaning here is that components parallel to the surface, so somewhere inside the surface, you've got 2 directions here. The parallel components of the electrical field, as before, are continuous across a boundary. Finally, the fourth one that I want to do is now the fourth equation, the Ampère-Maxwell equation, but now I will imagine that my surface carries a free current Kf like this, and this K is a surface current density, not a volume current density, because it's focused, it's concentrated on this surface here. So again, what this tells me is that if I look at the fourth equation, now I've got the H above minus the H below, dotted into L, and this now has to be equal to the enclosed free current. But you see, if I'm like this, then there is an enclosed free current inside that little Ampérian loop, right? The surface straddles the main surface here is perpendicular to the little surface of my Ampérian loop. So there is a current going through this, and this current is proportional to L. And essentially, you can convince yourself that if, let's say, this N is the normal vector to the surface, you've got a displacement here L, then you're interested in the perpendicular component to this, and you want to do that. So what this really becomes, it's K free. If I'm computing this thing here, it's K free dotted into the cross product between N and L. But actually, I can just rewrite this in a different order by just permuting this cyclically. So this is the same thing as the cross product between K free and N dotted into L. And you see now I equate both sides of the thing, and it's valid for any L, any direction that I want to have. So therefore, that gives me the condition that the parallel component of the magnetic field above minus below, so the discontinuity in the parallel component of the magnetic field H is proportional to the enclosed free current density And here I'm just putting n hat as the normal to the surface. Okay, so so these are generally valid, okay, at any boundary.